So now I want to ask you, how do I want to phrase this? Oh, which process here has energy going in and out of the system? I will put this question in what color? We'll do green. I'll put it here. Energy in/out of system. Question mark. Isovolemic. Do we expect energy going in and out of the system? Yes. And the reason being because internal energy is changing. So that must mean that there's some sort of transfer. So yes. Isobaric. Internal energy changes. So yes. Isothermal. A lot of students screw this up. Don't be those students. Isothermal, people think, oh, same temperature, that means it's not changing. No, it is not true, because when there is no change in temperature, that means heat is either being added to the system when the thing is expanding, or it's being taken away when it's compressing to make sure it maintains the same temperature all the time. So an isothermal reaction, you have to have systems, a lot of systems in place to make sure it maintains that same temperature. It's not an easy feat. So yes, the answer is yes, there is energy in and out of the system. Adiabatic, now you probably know what the unique thing is, it's going to be no. There is no energy going in and out of the system. And you're like, but wait, the temperature is changing. Yes, it is. Why is the temperature changing? Because when we choose to go from one volume to another volume and work is done, if we do not have a change in internal energy, that means that we have to be changing the temperature that's at to allow the same conditions, or to allow, what am I trying to say? Oh, the same internal energy conditions. So you can have that same internal energy all along the spectrum, but that means different volume, different heat, etc. So the answer here is no. Sweet, we're almost done here, so give me just a minute. The laws. I don't know how you remember them as, but I think of it as and these are the laws of thermodynamics. You can't win, you can't break even, and you can't get out of the game. Okay, so what does that mean? What does that mean? It's actually going to be very simple. If you can remember that mnemonic, you will not forget the laws of thermodynamics. I have not forgotten them in a long time. I mean, yes, I go and discuss them with students and whatnot, so it comes up every so often. But as long as you remember these, you can make the analogy to connect this to the equation that it's talking about. So what is that equation? You can't win. That means you can't make energy out of nothing. You need to get energy from something. Something has to be there in order for you to have it. So that's really just this equation. Okay? Change in U, or internal energy, equals Q minus W. That equation, I messed up the W. I don't have something to wipe it off with. Just use my finger. Okay. That equation, that change in internal energy equals Q minus W, is the essence of you can't win. You can't make energy out of nothing. You can't break even, which means that you can never have 100% efficiency. No 100% efficiency. Okay? And then last is you can't get out of the game. Not many people understand what the last law means, but it means that the entropy of the system always increases. Now, you're like, wait a minute, there's an adiabatic process here. Yeah, in actual reality, though, we don't have adiabatic processes, at least to my knowledge, because of the third law of thermodynamics, which is delta S of the universe will always be greater than delta S of the system. I believe I got that sign correct, but what it's saying is that the change in entropy of the universe will always be greater. There will always be more energy change in the universe than there is the system, aka the universe always has energy change. You can't not affect the universe by the process that you're doing. The universe always wins, so to speak. Actually, completely ignore that last sentence because it's going to confuse you with law 1. I believe that is it for thermodynamics. I guess bonus material, I'll just touch on some random topics of gas, expansion, non-expansion, ideal gas, etc. So that sound like a plan? Sweet. And the reason being is because people don't, or students don't fully understand the difference between an ideal gas and a real gas and what that really means. What are the implications? So hopefully I will remember all the differences, but let's go on. So an ideal gas, as you know, has certain expectations that you must know on the MCAT, and the three most important ones is 1, no intermolecular forces. No intermolecular forces in ideal gases. Now what does that mean? You already know the PV equals nRT equation, right? V equals nRT. That I just mentioned, that what was it? I lost my train of thought. The energy, the intermolecular reactions, the intermolecular forces do not exist in ideal gases. Well, in real life they do. As a result, the pressure will be affected. Now here is the interesting part. What do you think causes more pressure? A real gas or an ideal gas? Well, the trick is that it's actually the ideal gas that causes more pressure. And you're like, whoa, what do you mean? Well, if we imagine a container of a bunch of molecules, all those molecules have intermolecular reactions, correct? Correct. So that means they are constantly being pulled into the center because they're being pulled by the other molecules which exist in the center, not on the outside. As a result, all these molecules are being pulled towards the center. This kind of looks like a cookie. And that means when they go to hit the wall, they don't hit with as much force, aka they don't hit as much pressure. Good. So that there is an A and a B in the real gas equation. I don't remember the full one, but I believe that A is going to be with volume and B is going to be with pressure, and then B would be taking into account the intermolecular forces, just so you have some additional understanding beyond what you're given in the PV equals nRT. Cool. Now the volume. Ideal gas molecules have 0 volume, right? So we would expect the real gas molecules to have real volume. As a result, our container that might be like 1 liter, right, actually is not fully 1 liter when you're dealing with a real gas, because some of that space is the accumulation. Like if we would push all the molecules up into the corner, those molecules take up space. So you have to take that into account, and I'm pretty sure then you would say that volume equals the volume of your container minus A, which A would be then the, what's the word I was looking for, the volume of the molecules. Okay, so then if that one's minus, this one is a plus. I know it's very small, but bear with it. There are other variables like I think it's like this is the P plus B is over V squared or something, and whatever else. But I just want you to get the main concept here that you don't already know from Gen Chem, because they usually don't go over it. Let's see, what else? There is an assumption of no mass, but I don't really want to talk about that any more than I just did. There is the assumption of completely chaotic movements, completely random. There's one more like high yield MCAT one though. No intermolecular forces, no intermolecular forces, the volume. Crap. I'm probably going to pause this video for a second and go get to it because I'm blanking right now. Alright, just remembered elastic collisions. Every collision in the gas is completely elastic. You do need to remember that. What does that mean? So when you have non-elastic collisions, that means heat is actually given off. So in a real gas, you can give off heat from those non-elastic collisions. And then elastic collisions in the ideal gas means that all the energy is retained as soon as they hit off. Okay? I believe that was the last piece that I had to tell you about the difference between a real gas and ideal gas. And now you have about what I would say is 80% of what you have to know for thermodynamics on the MCAT in the chem section. And the rest of it is applying all of these concepts. So good luck to you. And again, this is KD, I guess we call it KD Chem, maybe KD Physics, whatever it happens to be. If you want more knowledge like this, subscribe to the channel, add some comments. If you have any critiques or if I got any of this information wrong for any reason, please let us know, or if there's any caveats in the information, again, please let us know. If you want any other material, you can go check out the channel. If you're looking for KD Psych, I am in the process of putting it on iTunes. Right now it is on YouTube, and so once I put it on iTunes, because there's like the luxury of having all the audio files or whatever, I'll like charge a small fee for it. But everything else, all the YouTube links, you can still get that. I'll just click it through the links and whatever. Let's see what else. I think that's about it. So I will see you next time.